Okay, in the 01.1 video that you watched, I made reference to the SI unit system, and that information is now somewhat out of date. As of May 20th, 2019, the SI system was overhauled. And I'd like to get into what the impetus was for that change, the philosophy of the new system, what the new definitions and the implementations of those definitions are, and some of the consequences of it. So, why change? The big reason had to do with lab reproducibility, especially for the kilogram. So, what does it mean for something to be lab reproducible? Reproducible. What that means is any idiot with a few $1,000,000, at least in principle, could build just as good of a second as any other idiot with a few $1,000,000. Just go to Atomic Clocks R Us, purchase yourself an atomic clock, way to go. You want yourself a meter, again, not a problem. Go ahead and set up a time of flight measurement, and you're good to go there. The problem was with the kilogram. The kilogram was not lab reproducible. It was a chunk of metal in France. And the problems with that, some of them are obvious. And for instance, what if someone were to ever drop it? You're trying to store this thing in a vault forever. You pull it out every few decades because you're afraid of it being mishandled. Every time you handle it, you are going to change its mass ever so slightly. So it creates this conundrum. You're only pulling it out every few decades because you're afraid of changing it, but since you're only pulling it out every few decades, you can't tell if any of the national copies have changed. So, whoa. So anyway, the comparisons have been fairly rare, but the most recent one was a little troubling in that we were starting to see a clear trend that the national copies of the kilograms were all getting heavier. Now, by definition, the international prototype of the kilogram, what is affectionately called Le Grand K, the blob of metal in France, by definition, its mass cannot change. But practically speaking, if most of the copies are drifting upwards in mass, you can't exclude the possibility that Le Grand K's mass maybe was decreasing a bit, or vice versa. In any event, it meant that the kilogram itself was changing, and that was something that we couldn't stand. There's also almost a target of opportunity thing, the Kelvin. With that one, the people working in thermodynamics had a nice practical standard involving a whole collection of triple points of different materials. The Kelvin itself is officially based on the triple point of water and absolute zero as the two reference points. But the people who were working on that were pointing out that they were having problems with this definition, trying to extend it into ranges at temperatures below about 20 Kelvin. It wasn't working as well as they would have hoped, and at temperatures above about 1300 Kelvin, they were having some problems. So, not as important as the issue with the kilogram, but well, maybe if you're working in thermodynamics, maybe it's more important. But certainly from a trade perspective, probably the change in the kilogram had people a little more worried. All right, so what's the philosophy for the new system? Interestingly, the new system is kind of like the way the old system was originally. What do I mean by that? In the old system, everything was based on the Earth. on the Earth itself or water, one of the primary components of the surface of the Earth. So as an example, the second was based on the Earth's rotation. It was 1/86,400th of a mean solar day. The meter was based off of the circumference of the Earth. The kilogram, once you had yourself a meter, you could you could say that the density of water was 1,000 kilograms per cubic meter, and you could build yourself a kilogram. The degree Celsius, which is related to the Kelvin by a constant factor of 273.15, was based on the thermal properties of water. Okay, so it's really elegant that we're letting nature dictate the units, which is a nice philosophical approach. Some problems with it. As far as this goes, as far as the Earth goes, its rotation rate is slowing down. And it's not round enough. That last part really affected the meter. They realized that they knew that the Earth wasn't round because since it's spinning, the equator is spread out a little more. So they based it on the distance between the equator and the North Pole. However, they found out that the Earth wasn't regular enough for that, so they had to pick a meridian. So they picked a meridian that went through Paris. They commissioned 3 surveys to check it out. Turns out that the second survey was the best, but they went with the results of the third survey. So the meter didn't perfectly match up with that when they standardized it out based on that survey. Water, if you remember from, sorry about this. Water, if you remember from chemistry, does a really good job of dissolving things. So that has the effect, in case of temperature, of changing freezing and boiling points. In the case of the kilogram, it affects the density of the water. So eventually, all of the standards were changed to the best approximations of these ideals, but to things that were more lab reproducible. Now, interestingly, though, so we've gone from the Earth and water dictating the units to a collection of arbitrary experiments, and now we're actually, in a way, going full circle. The idea now is that we are letting the universe itself dictate the units. So what do I mean by that? The idea here is that we will let the units be implicitly defined by properties of the universe. And the way this is done in practice is we're going to make several constants, physical constants, exact numbers. And in fact, in the process, we'll create 2 new ones. Now, as far as practical things go, the International Bureau of Weights and Measures will still publish bulletins with what they consider to be best practices. But in principle, you could use any technology you like to implement measuring something. So we should be done unless we discover that some fundamental constant isn't. This should be the last time that we need to redefine any of these things. So let's get into the definitions themselves. Oops. Redo. There. So let's get into the definitions themselves. We'll start with the second. Symbol S. This is one that's almost the same. What we did here is there is a new constant that's been defined. Specifically, it is the frequency. That's a delta. That is a lowercase Greek nu for cesium. This is the frequency emitted by that hyperfine transition in cesium-133. And this is defined to be exactly 9,192,631,770 inverse seconds. The inverse second is also known as the hertz, the unit frequency, and this is an exact number. All of these numbers I give you in this lecture will be exact. So we can reverse this around. We can go ahead and say we can solve this. We can solve this for the second. And you would get that the second is exactly equal to 9,192,631,770 over delta nu cesium. And that literally is the definition of the second now. So how does this differ from before? From before, it differs in direction. By this I mean before we said that a second is said to have elapsed when we count 9,192,631,770 oscillations coming off of this cesium-133 emission. Now we're flipping it around and saying, definitionally, this is the frequency. Measure the second however you like. So the current best practices are still going to be to use the cesium-133 atomic clock, but a lot of atomic physicists have floated the idea that maybe we should switch to rubidium atomic clocks. And with this, you could. The only thing you would have to do is you'd have to use your rubidium atomic clock. It would have to be calibrated using this cesium-133 emission. But once you calibrate it, hey, you have your new rubidium atomic clock. And if it measures things more accurately, great. At some future point, the International Bureau of Weights and Measures might change their circular saying what's best practices, but it opens up it's not tied to a specific technology. It opens up the idea of different technologies. In the same vein, but without having to create a new constant, is the meter. And the meter, once the second has been defined, the meter gets implicitly defined by setting the speed of light to be exactly 299,792,458 meters per second. And this was exact before because of the definition we had that said the meter was the distance light traveled in 1 over that number of seconds. But again, we've flipped the direction of it. Now we say that the speed of light is exactly this. You can solve it for a meter. So we can say 1 meter would be c times a second. We can put in the definition of the second, and you get this kind of awkward fraction of 9,192,631,770 over 299,792,458 times C over delta nu cesium. So that is the meter. And again, measure it however you like. The best practice is still a time of flight measurement, where you use an atomic clock to measure how long it's taken for a laser beam to travel some distance. Okay. Normally, when presenting this sort of thing, I would skip ahead. I would go and talk about the kilogram next, because that's sort of the classic order of these things. But I'm going to talk about the meter. So talk about the ampere first, just because I think it'll be a little easier for us to loop back and talk about the kilogram if we get the ampere under the belt. So for the ampere, again, same kind of idea. We're going to be setting a constant. And yes, the ampere is the base unit. I know that you learned that an ampere is a coulomb per second, but for historic reasons, the ampere is the base unit, and the coulomb is actually the derived unit. So anyway, the physical constant in question is the fundamental quantum of electric charge. It is now set to be exactly 1.602.176.634 times 10 to the negative 19 ampere seconds. And the derived unit for that is the coulomb. Okay. The way the ampere has usually been measured practically has been to use Ohm's law and use special quantum devices that allow you to very precisely know your voltage and your resistance in order to get your current. If we do the same exercise here, we can go ahead and solve this for the ampere, and then we can go and stick the definition of the second in. And if we do, we get that what we mean by an ampere in the new regime is that it is exactly E times delta nu cesium over, I'm not going to bother multiplying numbers out, I'll just leave them out, 1.602.176.634 times 10 to the negative 19, oops, times 9,192,631,770. Okay. And so that's what we mean by an ampere. And sorry about that right there. Now we'll go and loop into talking about how the kilogram changed. This is probably the biggest change. Oops. The kilogram is now implicitly defined through Planck's constant, which is a quantum mechanical constant. If you've taken modern physics, you know about this one. It is now defined to be exactly 6.626.07015 times 10 to the negative 34 kilogram meters squared per second. And this is usually, we use the derived units and say it's a joule second. Okay, you can do the same kind of exercise you have before. You can go ahead, solve for the kilogram. You can insert our solutions for the meter and the second that we had before to get that, what we now officially mean by a kilogram is the fraction 299,792,458 squared over 6.62607015 times 10 to the negative 34 times 9,192,631,770 H delta nu cesium over c squared. So the idea is coming from E equals mc squared here. If you've had modern physics, you know that the energy of an oscillator is Planck's constant times the oscillation frequency. So there's an energy divided by c squared from E equals mc squared. You're left with a mass. So this is officially what we mean by a kilogram now. Great. But how do we do this one practically? Turns out that this is probably the biggest change in implementation of things at the moment. There's a new device being used for this. It's a thing called a Kibble Balance, after the guy who came up with it. You'll also see it in the literature as a watt balance. And the idea here is that you can think of it as a balance where you put a mass in one pan, so you have a gravitational force, and then you create a known magnetic force, which to do that, you're going to need a current that you understand very well. This is why we had to improve the definition of the Ampere. Balance them out, and you can weigh something now. These, as a practical matter, these balances are insanely expensive. There is one at the National Institutes of Standards and Technology in Gaithersburg, Maryland, the U.S. standards body. I'm sure some other national governments might get around to building them, but these things are very expensive. For a long time, I expect you're only going to be seeing a few of them on the surface of the Earth. So it's probably going to be quite a while before, say, a company that actually makes weighing devices like O-House, as an example, is going to have a Kibble Balance just hanging around in their facility. So there will still have to be artifact comparisons. They'll have to happen as a practical issue. So now the idea is you can build an artifact, weigh it with your Kibble Balance, and then you can do artifact comparisons from that artifact. In order to make the artifact, we'll find out that that we had to tweak the definition of the mole while we're at it. Okay. So but we'll do that when we get to the mole. For now, though, we will talk briefly about the Kelvin. It was defined as in reference to absolute zero and the triple point of water. That no longer is the case. Now it's a constant from thermodynamics. Boltzmann's constant is now exactly 1.380649 times 10 to the negative 23rd kilogram meters squared per Kelvin second squared. And that whole mess is a joule per Kelvin. We can do the same process as before. We can go ahead and put in the previous solutions we have for kilogram, meter, and second, solve for Kelvin. When you do, you get that 1 Kelvin is now exactly 1.380649 times 10 to the negative 23 over 6.62607015 times 10 to the negative 34. times R 9,192,631,770. And all of that times the fraction H delta nu cesium over Boltzmann's constant. All right. And officially, that is what we mean by a Kelvin now. So how things change practically? The answer is for the next few years at least, probably not at all. Thermometers have been calibrated by a list of triple points of different substances, one of which was water. The difference now is that the triple point of water is no longer an exact number. It's now an experimental value. But we're still using that list of triple points to calibrate thermometers. In the near term, however, there are quantum devices that are in development that what they will do is they'll very precisely measure the thermal energy of the device, and then we can say that we can then relate the thermal energy to the temperature via Boltzmann's constant. And those are coming up soon, so watch this space. Okay. We also had a change, as I foreshadowed, to the mole. It's now defined through Avogadro's number, which is now an exact number. It is now exactly 6.022140076 times 10 to the 23rd inverse mole. And that is an exact number now. You can, for completeness, we can flip it around, solve it for the mole to say that it is 6.022140076 times 10 to the 23rd over Avogadro's number. Okay, so the big deal here, and so the change that we had, and we'll touch on this a bit more in a bit. Avogadro's number is now officially just a number. The link it had to the carbon-12 isotope has been broken. And what this is actually going to allow us to do is, if you remember I was talking about the kilogram, you're still going to have to make practical kilograms that can still be weighed with balances so that companies like OHouse can calibrate their equipment. Chemists came up with a very clever approach where they can make extremely pure spheres of silicon-28 atoms, where they pretty much know, they know to very high precision how many atoms are actually in these spheres. So by setting Avogadro's number to an exact number, this allows them to build these spheres to be very close to a kilogram. So you go ahead, you make one of these spheres, you weigh it in a Kibble balance. You then use these spheres as practical standards to calibrate everything else. Okay, for completeness sake, may as well talk about the Candela. This is also one where there's a new constant. And again, this is a case where we've reversed the direction of things. So the constant is literally called K sub Candela. And this is because the Candela is a very made up unit that's tied in to sort of an approximation of how the human eye perceives light intensity. This is of importance to people who work in optics. So if you take an optics course, you may run across this. But most of the time, you'll probably just work in intensities like watts per square meter or something like that. But anyway, this constant is defined to be 683 Candela steradian seconds cubed per kilogram meter squared. That's a lumen per watt. So it's 683 lumens per watt. Again, this is a reversal of direction, but isn't really a substantive change. Okay, so what are the consequences of all of this? Probably the biggest one, and this is huge, is there are no more artifacts. This is big. In principle now, if we were to ever, say, make contact with some extrasolar civilization, we could transmit all of our scientific knowledge by just saying, hey, this is the list of constants that we use. The units are are defined implicitly through that, and they'd be able to work absolutely everything out without having to figure out, without having to make reference to a blob of metal in France when they've never been to France. Also, more importantly, we're no longer petrified about the possibility of somebody dropping that blob of metal. There are some other ones, though, that you may want to be aware of because they might affect you in other classes, maybe someday. Probably not much unless you're doing super high precision things. But one of them is epsilon naught and mu naught from electricity and magnetism are no longer exact numbers. It is still true that the speed of light is equal to 1 over the square root of epsilon naught mu naught. That's still good, but mu naught is no longer exactly 4 pi times 10 to the negative 7 Tesla meters per ampere, for instance. In fact, there's already been one high precision measurement done to see what the deviation off of it is. Now, as a practical matter, these deviations are extremely tiny. So unless you're doing ultra high precision stuff, this is probably not going to matter. But these are no longer exact. Possibly a little more importance is the unified mass unit or the atomic mass unit. Chemists also call it the Dalton. So U was the old symbol, Dalton. They're trying to get us all to write DA for Dalton now. This is in a bit of a state of flux right now. Because it was defined as the old definition. In fact, it's still officially the definition of these. It's defined as being 1/12 the mass of a carbon-12 atom. But it is no longer the case that a mole of carbon-12 weighs 12 grams. That's technically no longer correct. It's going to be some number painfully close to 12 grams. And currently, whatever that number is, it's within experimental uncertainty of 12 grams. So the people who professionally worry about this have kicked this down the road a little bit. But at some point, either the atomic mass unit will have to, either the one or the other or both of these will be redefined so that we're back to saying that a mole of carbon-12 is 12 grams, or we'll just make these now experimentally attainable numbers and say it's the 12th of a mass of a carbon-12 atom. That's again a watch this space kind of thing.